Electromagnetic energy that travels in waves. Not all light is in the visible spectrum. Light is a form of energy that we can see, which travels in waves through space.
Imagine trying to tune into your favorite radio station, but the dial is slightly off, so you hear static instead of clear music. Just like a radio, light consists of many different stations or wavelengths, not all of which we can tune into or see with our eyes. The visible light we see is like the clear music when the radio is perfectly tuned, while the static represents the vast range of electromagnetic energy, like ultraviolet or infrared, that exists but isn't visible to us.
Visible light produced when phosphor is hit by ultraviolet light. Fluorescent light. Fluorescent light is created by using ultraviolet light to excite a coating inside a bulb, which then emits visible light.
Imagine trying to read a book in the dark without a flashlight. You can't see the words until you shine a light on the page. Similarly, in a fluorescent light, the phosphor coating inside the tube remains invisible until it is illuminated by ultraviolet UV light. Just as the flashlight reveals the words on the page by shining light on them, the UV light excites the phosphor, causing it to emit visible light that brightens the room.
Light produced when a metal is heated until it glows. It was used in old light bulbs. Incandescent light is light that comes from heating a material until it glows.
Imagine trying to get warm by wrapping yourself in a cozy blanket on a chilly night. Just like your body generates heat and transfers it to the blanket, causing it to warm up and provide comfort, an incandescent light bulb works by passing an electric current through a metal filament, heating it until it glows and emits light. The connection is that both scenarios involve applying energy to a material, your body to the blanket, and electricity to the filament, to produce a desired effect, warmth in one case and light in the other.
The image of a distant object created when refracted light passes through air layers of different densities. Mirage. A mirage is an optical illusion where light bends in the air, making objects appear displaced or distorted.
Imagine you're looking at a spoon in a glass of water, and it appears bent or broken at the surface. This visual trick is similar to how a mirage occurs when light bends as it passes through air layers with varying temperatures and densities. Just like the water changes the path of light, causing the spoon to appear distorted, different air layers in the atmosphere refract light, creating the illusion of distant objects seeming closer or appearing where they aren't.
A material that does not let any light pass through. Opaque. In simple terms, opaque means you cannot see through it because it blocks all light.
Imagine trying to have a conversation with a friend over the phone, but there's no signal, and your words don't reach them at all. This situation is similar to how opaque materials behave with light. They completely block any light from passing through, just as the lack of a signal prevents your voice from getting through. In both cases, whether it's your voice or light, the intended message or beam is stopped entirely, leaving no way for it to continue to the other side.
Occurs when light hits the boundary between two materials but is reflected back. Total internal reflection. It is when light completely reflects inside a material instead of passing through, like light bouncing back into water from its surface.
Imagine you're trying to walk through a crowded room, but when you reach a particularly dense group of people, you're pushed back the way you came. This scenario is similar to total internal reflection, where light, instead of passing through the boundary into a different medium, is reflected back into the original medium. The crowded room is like the boundary of two materials, and just as you get redirected back because you can't get through, the light is reflected back because it can't cross the boundary at a certain angle.
Allows some light to pass through but scatters it. Translucent. Translucent materials let light through but blur it so you can't see clear images.
Imagine trying to read a book with a window shade partially drawn, letting in just enough sunlight to illuminate the room, but not enough to see everything clearly. This scenario is similar to how translucent materials work, as they allow some light to pass through but scatter it, making objects on the other side appear blurry or indistinct. Just like the window shade diffuses the sunlight, a translucent material diffuses the light passing through it, providing partial visibility and a softened view.
Allows light to pass through. Transparent. In simple terms, transparent means a material that lets light pass through so you can see clearly.
Imagine trying to listen to a friend at a busy cafe, where the background noise makes it hard to hear them clearly. This is similar to how light interacts with different materials. Just as your friend's voice needs a clear path to reach your ears, light needs a clear medium to pass through for us to see objects on the other side. In this analogy, a transparent material like glass acts like a quiet room that allows sound or light to travel through without interference, making it easy to perceive what's beyond.
The passage of light through a material. Transmission. Transmission is when light or other forms of energy pass through a material without being absorbed.
Imagine trying to walk through a busy crowd at a concert. Just as you navigate your way through the throng of people, occasionally bumping into someone or having to squeeze through tight spaces, light passes through a material, interacting with particles within it. In this analogy, you are the light, the crowd is the material, and the way you weave through the crowd mirrors how photons travel through and interact with the atoms or molecules in a material, sometimes bouncing off, slowing down, or passing straight through.
The transfer of energy from a wave to an object, like sound energy when it hits a wall. Energy absorption. In simple terms, energy absorption is when an object takes in the energy from a wave or impact, reducing the energy's effect elsewhere.
Imagine trying to carry a large load of groceries from your car to your kitchen in one trip. Just as the groceries are transferred from your arms to the counter, energy from a wave, such as sound, is transferred to an object, like a wall. In both cases, there's a transfer of something from one point to another. Groceries to the counter, and energy to the wall. Where the object receiving the load, your counter or the wall, has to absorb and hold. What is being transferred, groceries or energy?
States that the angle of incidence is equal to the angle of reflection. Law of reflection. In simple terms, the law of reflection explains how light bounces off surfaces in a predictable way.
Imagine you're playing a game of pool, trying to sink a ball into a pocket by bouncing it off the table side. Just like when you aim the ball at the cushion and it bounces off at the same angle, light behaves the same way when it hits a mirror. In this analogy, the pool ball is like a beam of light. The cushion represents the mirror, and the way the ball bounces off at an angle equal to how it hit is just like how light reflects off a surface, illustrating the law of reflection where the angle of incidence equals the angle of reflection.
Reflection of light at many angles by a rough surface. Diffuse reflection. It occurs when light hits a rough surface and scatters in many directions, making objects visible from various angles.
Imagine trying to wrap a gift with crumpled wrapping paper instead of smooth, flat sheets. Much like how the crumpled paper causes the light to scatter in different directions instead of reflecting neatly, a rough surface causes light to bounce off at many angles. Just as the uneven texture of the paper disrupts your ability to create a smooth, uniform package, the irregularities on a rough surface scatter light in various directions, leading to diffuse reflection.
A mirror with a surface that curves inward, concave mirror. A concave mirror focuses light to a point and can make images appear larger when viewed up close.
Imagine trying to scoop ice cream from a container, but the scoop is flat and doesn't quite gather the ice cream effectively. This is similar to how a concave mirror works, because just like a curved ice cream scoop gathers and focuses the ice cream into a single ball, a concave mirror collects and focuses light rays toward a single point. The inward curve of the mirror acts like the curve of the scoop, directing and concentrating the scattered light beams, just like the scoop directs the ice cream, making it more effective at gathering and focusing them.
The point at which light rays converge after passing through a lens is called the focal point. In simple terms, the focal point is where light meets after being bent by a lens to create a clear image.
Imagine trying to listen to a conversation in a crowded room where everyone is talking at once. Just like how you focus on one conversation amidst the noise by directing your attention, a lens gathers scattered light rays and converges them to a single focal point. In this analogy, your ears act as a lens, filtering out other sounds to focus on a specific conversation, much like how a lens directs light rays to converge at the focal point.
A mirror with a surface that curves outward, convex mirror. A convex mirror is a type of mirror that bulges outwards, making objects appear smaller and providing a wider field of view.
Imagine you're in a crowded room, trying to see as many people as possible without moving around. Just like how standing on your tiptoes can give you a broader view of the room, a convex mirror allows you to see a wider field of view by curving outward. The outward curve of the mirror acts like your elevated position, capturing more of the surroundings and reflecting it back to you, helping you see areas that would otherwise be out of sight.
A transparent object with at least one curved surface, light bends when passing through it. A lens is a tool that focuses or disperses light rays.
Imagine you're trying to get a marble to roll straight down a bumpy, uneven path. Just like the path changes the marble's direction, a lens redirects light because of its curved surface. In both cases, the unevenness of the path or the curvature of the lens changes the trajectory. The marble gets nudged in different directions by the bumps, while the lens bends the light as it passes through, focusing or spreading it out depending on the curve.
A lens with a center thicker than its edges. Convex lens. A convex lens bends light rays inward to focus them at a point, making objects look larger.
Imagine trying to focus sunlight on a piece of paper to start a fire using a magnifying glass. Just like this task requires concentrating light rays to a single point to generate heat, a convex lens does the same by bending light rays that pass through it to converge at a focal point on the other side. The center of the lens is thicker than its edges, which allows it to bend the light inward, much like how the curved glass of a magnifying glass directs sunlight to a specific spot, concentrating its energy to achieve the desired effect.
A lens with a center thinner than its edges. Concave lens. A concave lens is a type of lens that spreads out light rays, making objects appear smaller.
Imagine you're trying to fit a large, fluffy pillow into a tight, narrow pillowcase. Just like how the pillowcase is thinner in the middle to accommodate and shape the pillow, a concave lens is designed with a center that is thinner than its edges to redirect light. In this analogy, the pillowcase represents the lens, guiding and focusing the pillow, light, by narrowing in the center, which mirrors how a concave lens spreads light rays outward, causing them to diverge.
A receptor cell in the retina that works in dim light but cannot detect color. Rods are cells in the eye that help us see in low light conditions, but they don't perceive color.
Imagine trying to find your way around a dimly lit room at night. Much like how your eyes adjust to see basic shapes and movements in low light without distinguishing colors, rod cells in the retina function similarly. Just as your eyes focus on recognizing outlines and objects rather than colors in the dark, rod cells are specialized for detecting light intensity and movement, but are not equipped to perceive color, allowing you to navigate in low light conditions without the full spectrum of vision.
The retina cells that work in bright light and help us see color. Cone cells. Cone cells are specialized cells in the eye that allow us to see colors and fine details in well-lit conditions.
Imagine trying to read a book in a dimly lit room where the words on the page are hard to distinguish and colors appear dull. This scenario is similar to how our eyes struggle to perceive colors and details in low light conditions without the help of specialized cells. The connection here is that just as bright light makes it easier to read and see colors vividly, cone cells in our retina are responsible for processing bright light and enabling us to see colors clearly. These cone cells act like the bright lamp that illuminates the text and colors, allowing us to experience the world in vibrant detail.
A telescope that uses convex lenses to focus light from distant objects. Refracting telescope. A refracting telescope uses lenses to bend light and make distant objects appear closer and clearer.
Imagine trying to read a sign from far away that appears blurry and too small to understand. Just like how you might use a pair of binoculars to bring the sign into focus and make the details clearer, a refracting telescope uses convex lenses to gather and focus light from distant objects, making them appear larger and more defined. In this analogy, the binoculars represent the telescope's lenses, which both serve the purpose of collecting light and focusing it to help us see distant details more clearly.
A telescope that uses concave mirrors to reflect and focus light from distant objects. Reflecting telescope. A reflecting telescope is a device that uses mirrors to gather and focus light from stars and planets for viewing.
Imagine you're trying to see your reflection clearly in a spoon. Just like a spoon's concave surface gathers and focuses light to show your face more clearly, a reflecting telescope uses a concave mirror to collect and focus light from distant objects. In both cases, the curved surface, the spoon or the telescope mirror, captures scattered light and concentrates it to a point, allowing you to see the details more clearly.
An instrument that uses lenses to magnify small objects. A microscope is a tool that helps us see tiny details of things invisible to the naked eye.
Imagine trying to read the fine print on a contract without your reading glasses. Just like squinting and holding the paper closer to see the tiny details, a microscope uses lenses to bring small objects into a larger view. In both cases, the use of lenses, glasses, or microscope helps magnify and clarify details that are otherwise too small to see clearly, allowing us to understand or examine the finer points more effectively.
A device that produces a narrow light beam of a single color and frequency. Laser. A laser is a tool that emits a concentrated beam of light, all in one color, used in things like cutting materials or medical surgeries.
Imagine trying to get a group of people at a crowded party to focus on singing the same song at the same time. This is similar to how a laser works, where it aligns countless light waves to move together in perfect harmony. Just as you need everyone to synchronize their voices and sing in unison to produce a clear and focused song, a laser organizes light waves of a single color and frequency into a tight, directed beam, ensuring they all sing the same note, creating a powerful and precise output.
A three-dimensional photograph created using lasers. Hologram. A hologram is a picture that appears in 3D and is made with laser light.
Imagine you are trying to recreate an entire jigsaw puzzle using only a few key pieces. Just as each puzzle piece contains part of the whole picture, a hologram is like capturing every angle of an object using laser light, storing a complete 3D representation in a single image. Just as each piece of the puzzle helps you visualize the entire image when put together, each tiny part of a hologram contains information about the whole object, allowing you to see it in 3 dimensions.
The reflection that occurs when parallel light rays hit a smooth surface and every ray is reflected at the same angle, regular reflection. Regular reflection is when light bounces off a smooth surface in a uniform direction, like a mirror.
Imagine trying to stack a series of coins neatly on a perfectly level table. Just as each coin remains aligned and reflects the overall neatness of the stack when placed on a smooth surface, parallel light rays hitting a smooth surface during regular reflection behave similarly. In this analogy, the coins represent the parallel light rays, the level table is like the smooth reflective surface, and the aligned stack illustrates how each light ray is reflected at the same angle, maintaining order and consistency.
A flat mirror that produces upright images of objects. Plane mirror. A plane mirror is a smooth, flat surface that reflects light evenly, creating a clear image right side up.
Imagine trying to find the right size for a new pair of shoes online without being able to try them on first. Just like how you rely on the shoe size chart to accurately reflect what fits your foot, a plane mirror reflects an image that matches the size and orientation of the object in front of it. The connection lies in both scenarios, providing a direct and unchanged representation. The shoe size chart gives a straightforward guide to fit, and the plane mirror offers an upright and true-to-size image of the object, making understanding and comparison straightforward in both cases.
The opening at the center of the iris, through which light enters the eye. Pupil. The pupil is the adjustable opening in the eye that controls how much light enters.
Imagine trying to adjust the blinds in a room to let in just the right amount of sunlight so you can see comfortably without being blinded. This is similar to how the pupil in your eye works. It adjusts its size to control the amount of light entering the eye, ensuring you can see clearly without being overwhelmed by brightness. Just like you manipulate the blinds to manage light levels, in a room, your pupil expands or contracts to regulate the light entering your eye, maintaining optimal vision.
The light-sensitive layer at the back of the eye, it contains rods and cones. Retina. The retina is a part of the eye that detects light and sends signals to the brain to create visual images.
Imagine trying to catch the right episode of your favorite TV show without a guide to tell you when it's on. Just as you rely on the TV guide to decipher which shows are playing and when, the retina serves as your eye's guide, interpreting light into signals your brain can understand. The rods and cones in the retina are like the guide's listings. Rods help you see in low light, like finding the right show at night, while cones let you see colors clearly, ensuring you enjoy the full spectrum of your favorite episodes.